Guys, this video is going to be talking about actual moving objects. I know we had promised you that physics was the study of motion, and we've been talking about nothing except for accuracy, precision, sig figs, rounding, all of those things. Today we are actually, or in this video, we're actually going to be talking about things that are moving. So now usually on the first day of class, I ask, am I moving? How can you tell if I'm moving? It kind of all depends on your perspective. So usually in class it sparks a debate. Like people are like, oh, you're moving, things in your, your blood is moving, your hair is moving, when I make emphatic points. But somebody eventually gets my point, is that yes, I am moving even though it looks like I'm standing still. Why do I look like I'm standing still to you when you're watching me in my classroom? And how am I moving? Well, you don't feel it or realize it sometimes, but the earth is constantly spinning. But you can't actually tell that we are spinning because we are all moving together. I kind of compare it to when you're in a car and you're driving really fast and you look at your friend and it doesn't look like they're moving, but they're actually moving just as fast as the car. Because you're all moving together, you don't notice a difference. So we can't tell if an object's moving or not unless its distance from a reference point is changing. So I can walk around the classroom and you can tell I'm moving spots based on how close or far I am from you, or from the projector, or from anything. You're comparing me to another object, and if that distance changes, you know that I'm moving. So I want to reference this first slide. I apologize for all the technology stuff, but this was normally a clearer little video that we would see in class, but it's Forrest Gump. If you don't know who that is, great movie, you should watch it. But is this person moving? Can you tell? Well, yes, the location of all the different objects behind him are changing, and he's no longer in front of the mailbox, he's now on the street, he's definitely moving. Is he moving fast? Well, that also depends on what you're judging by fast, but what could I measure to be able to know for sure if he's moving fast? Hopefully some of you said distance. It's how far he can run, right? But it doesn't just depend on how far he can run, it also depends on how much time it takes him to run that far, right? If he takes very little time, he might be considered fast. Or if he can run very far, maybe that's really fast, but it depends on both. So before we go into that, I'm going to give you a few more definitions. I know I said we were done, not quite, but there are a couple of different types of measurements we can take. A scalar is a type of measurement that only describes how big something is, versus a vector measurement is something that gives me a direction in addition to how big something is. So when I think, how I remember the difference, when I hear the word scalar, I think of the word scale. And I think about like a scale in your bathroom. When you step on it, it tells you a number. Sure, it tells you, maybe if you compare it to yesterday that you're bigger or you're smaller, but really in that instance, it just tells you a number. So a scalar just tells you how much of something you have, or the magnitude or the size of the object. It doesn't tell you anything else. A vector will tell you that much north, or that much bigger, I guess, in a way you could think of it like that. It definitely tells you something other than just the amount or the number or the size. So, two different things we can measure to tell how fast we are going. Distance, displacement, are very similar to each other, and they measure how far something goes. So in this class, we are going to talk about distance, and we're going to measure distance, and we are going to use the symbol d, lowercase d, to abbreviate distance, and that is how far something goes. It is a scalar quantity, meaning that it only tells you an amount, so amount only. How far you went, how big your distance is. So no direction associated with it. In this class, we will use meters to measure distance. So no miles. Every now and then we'll reference miles, by the which are abbreviated MI in this class, so do not confuse that with M for meters. And an example of a scalar measurement for distance would be the car traveled 200 meters. So we might also measure the displacement an object moves, and the symbol for which can change based on the direction. So this triangle symbol is the Greek letter delta, and it means change in. So displacement is also how far something travels, but it also keeps track of direction, which is why we have delta x and delta y. Maybe you're wondering why delta x and why delta y. Think to math class. We have axes. This is the x direction and this is the y direction. And in the real world, we can have something that moves sideways in the x direction. We can also have something that moves up and down, and spoiler alert, we can have something that does both. Eventually, we will get there. Not yet. But that is why we have two different displacement symbols. We might be talking about something moving sideways in the x direction or something moving up and down in the y direction. At first, for the most part, we'll pretty much stay with delta x just because we're going to start off just moving in one direction, side to side. But be ready for that. Displacement is the exact same thing as distance. It's measured in meters. The only difference is we are very specific about that direction. So, for instance, the car traveled 200 meters east. That would be a vector measurement and technically a displacement instead of a distance because it's telling me where the car ended up. It's telling me a where in addition to a how far. It's more specific. Think of displacement as how far an object has been displaced. Yes, definitely a fan of looking at vocab to make sure you remember the meaning of some of these weird new terms. How much I am displaced, how much I have shifted from my original position is a good way to think of displacement. So let's do some math examples. The car travels 200 meters to the left and then 300 meters to the right. I like to get into the habit of boxing or underlining specific information. So 200 meters to the left and 300 meters to the right. What is the distance the car traveled? As you go through the notes, I do want you to pay attention that sometimes we will give you the answer to the notes so you can check yourself as you go. Please ask your teacher if you don't understand why something is an answer to something. So I like to also draw a picture in this class. This example might be easy for you, but they will get trickier. So if you're stuck, drawing a picture helps. So 200 meters to the left, I'm drawing it going to the left, and then it travels from there 300 meters to the right. I need to make sure to draw that arrow longer than 200. Be sure to draw an accurate picture. If you say 200 meters to the left and then 300 to the right, and you draw them about the same size, it looks like I ended up back where I started, and we know that's not the case, so please be careful. Draw them almost to scale, about to scale. So what is the distance the car travels? Well, that's easy. Total distance is just all of those added together. He traveled this whole way, 200 plus 300, so that is 500. But now, what is the car's displacement? And how is displacement different from distance? So displacement is literally where he is compared to his original position. And if you look at this nice picture that we drew, maybe you can figure out that since this distance is 200, he ended up 100 meters to the right. Kind of nifty, huh? So how much has he been shifted from his original position? If he started here, he ended up 100 meters to the right, or you could say 100 meters in the positive direction. And I'll explain why that's positive if you don't quite get it yet. But how is displacement different from distance? I like to think of it as comparing steps. So maybe you have like a Fitbit or your Apple iWatch or some other device that measures your steps, and let's say you get up out of bed and you have a really good day. You walk like 12,000 steps. So 12,000 steps would be your distance. But if you climb back into the same bed at the end of the day, what is your overall displacement from when you woke up to when you went back to bed? Your position ultimately has shifted none. You haven't really displaced yourself that much by the end of the day. So that's kind of the difference between the two. But let's talk a little bit about a math equation for this, because some of you probably didn't like how I did this in my head, even though it was a simple example. Let's talk about the math. So how did you calculate total distance traveled? Well, you probably use this equation. You just added all your distances together, which is great. Displacement equation is a little bit tricky. Technically, if you remember from math class, any change in is usually final minus initial. And sometimes that initial I'm going to use the symbol sub-zero, so don't be afraid of that. If you see sub-zero, that means the same thing as initial, so just be aware. But delta is always final minus initial position. And that was tricky in that example because your initial position, maybe we say we started at 0, and your final position, you kind of had to calculate to put into this equation. So final position, we already knew it was 100 minus 0, so my displacement is 100. And I don't really like that. That equation is useful, but only when you don't start at 0 and you kind of know where you end up. So I have a made-up equation. It is a Miss Bailey equation, so you can use it if you like it, but I like this distance equation up here where you add the total distances. You can also add individual displacements together to get the total displacement. So like before with the previous example, you could just plug those individual displacements in to solve for the total displacement. So as an example, I'm sorry, I'm scrolling all over the place. I'm just going to use the example we already used. It was 200 meters to the left. How could we show left with just numbers? Maybe with symbols. I would use negative. So 200 meters to the left, and I'll write left, plus 300 meters to the right. I will make positive, and I'm just using parentheses to be extra careful. What do I get when I add those two numbers together? Well, I get positive 100, which, oh my gosh, is the same thing as 100 meters to the right. So that's kind of an equation. It's not a real equation. It's not going to be on your formula sheet, but it's a way to find total displacement if you're given pieces of that, like little individual displacements. You can just add them together. Just be sure you keep track of that direction with a positive or negative and don't mix those up. And the sign you get at the end will be your final direction at the end. So that's kind of nice. All right, so stuff to remember. Graphing, we are going to talk about graphing. So in a video or two coming up, you will experience graphing. Don't get too comfortable. It will start getting more challenging, but don't forget rules from math class. Typically to the right was positive and to the up was positive, and down and to the left were negative. Technically, you can make whatever direction you want positive or negative, but I find if you mix it up, sometimes you mix yourself up. So I like to keep it all the same. Just think of math class, up and to the right are positive, down and to the left are negative. Just keep that in mind whenever we're doing vector math. So now we have speed and velocity, and you've probably also heard of these two values before, but maybe didn't realize that they were different from each other and used them interchangeably. They are very similar, but the way that distance and displacement are similar but different, speed and velocity have the same kind of relationship. So they both measure how fast something is moving, but speed is a scalar and does not have a direction associated with it. So no direction for speed. But they're basically the same except for that direction. So we now have a math equation. Woohoo! We can do some math and physics. Speed is distance over change in time. We will usually write that as speed equals distance divided by time. And we will measure speed using meters per second, or meters divided by seconds. You can see where we got that if you kind of pay attention to the units in the equation. Distance is measured in meters, time is measured in seconds. Meters divided by seconds are where we get those measurement values for speed. Great. So velocity, again, is the same thing, but it's how fast it's moving in a given direction. And you're going to notice that both of these equations, there should be a line right here to show divided by. You're going to notice both of these equations, I'll just go ahead and write the speed equation right here, are exactly the same. The only difference is, since velocity is a vector, it's going to use that vector measurement of how far something travels. It's going to use displacement. Speed uses distance, but they're pretty much the same equation because they're pretty much the same thing, just that distance is different. And look, they're even measured with the same thing, which maybe you remember, distance and displacement are measured with the same thing. Great, we have a few math examples and then we will move on. A car moves 200 meters to the left, draw a picture, box your numbers, do something, and then 300 meters to the right. Again, draw that relatively to scale. If it takes 100 seconds to do this, what is the car's average speed? I'm going to take a moment to kind of explain a problem-solving strategy that is going to seem unnecessary here because these are pretty easy, but it's a good habit to be in for this class. So I like to go through and label information that the problem tells me, especially if you're bad at word problems. Go through and do this. So 100 seconds, that is telling me a time. 200 meters to the left and 300 to the right, that's telling me a distance or a displacement since they gave me directional values. And we are looking for speed. And I know it seems silly to write that, speed is my question mark, but eventually we're going to have a lot of equations that you have to pick out the right equation that's going to help you solve this problem. And if you know what you're looking for, it'll be much easier to pick out what equation you need to solve for it. Right now we only have 2 equations, and since I'm looking for speed, I know I'm going to use my speed equals distance divided by time equation. So what do I need to figure out speed? Well, I need the 2 things in the equation. I need distance and I need time. Well, if you remember, we kind of did the first part of this problem already. We know distance is 500, and I'm going to go ahead and write displacement since we already solved for it, is positive 100. So super easy from here, I can just plug and chug. My distance is 500 meters, and my time is 100 seconds. So that's pretty simple math. It's just 500 divided by 100 is 5 meters per second, which is the answer down here. So the next part of the problem asks, what is the average velocity? Velocity is what I'm looking for that last part, is displacement divided by time. I need to know displacement, which I happen to know. The time is still the same. And since velocity is a vector, I need to include a direction, positive, right, up, down, some form of direction. But the velocity of the car is positive 1 meter per second. Make sense? Cool. Next example, the speedometer in a car also has an odometer that records the distance traveled. If the odometer reads 0 at the beginning of the trip and 35 kilometers a half hour later, what is the average speed? We are looking for speed. If it helps, write down that speed equation so you know what else you need to find to solve for speed. Well, I need to know distance and I need to know time because those are the 2 things in that equation. They tell us the distance is 35 kilometers, which is great. However, in this class, we're only going to use kilometers sometimes when it specifically asks for it. When you're not sure, convert to your standard units, convert to meters. So I'm going to do a really quick dimensional analysis chart right here, just to give some of you a refresher for those of you who don't remember how to convert. So that would be 35,000 meters for my distance. And my time is a half hour. So you could write 0.5 hours, or I'm just going to write 30 minutes. But that time is also not our standard unit that we use. It's in minutes, and we use seconds. So I'm going to set another dimensional analysis chart up to convert from minutes to seconds. I get rid of those units I don't want, and I'm left with what I do want. So that's about 1,800 seconds. But now I have the units I want, so it's basically just going to be 35,000 meters divided by 1,800 seconds. When you plug that into your calculator, you're probably going to get a funky number. 35,000 divided by 1,800. That's 19.44444, but again, how do you know what to round to? You should be using your sig fig rules that you learned from a previous video, or maybe your teacher helped you with. So since there are 2 sig figs in that 35, and even when you convert, if you notice, if you keep your proper sig figs, they kind of stay the same. But the smallest amount of sig figs I have in either of these numbers, 35,000 and 1,800, is 2. So I should round to 2 sig figs. And usually that's a good rule of thumb. Whatever you start with is what you should end up with. Whatever the problem gives you is what you should end up with. So 2 sig figs would be, so I would round 19.44444 repeating. I would round that to 19. And don't leave your units, don't leave your numbers empty unless a quiz or a test or something tells you specifically to leave it empty. Usually include your units. All right, last example. If a cheetah can maintain a constant speed of 25 meters per second, how many meters will it travel in 1 minute? Well, a minute is a time. They gave us speed this time, so that's a little different. So I know the speed is 25 meters per second. I know the time is 1 minute. I can convert that in my head. I'm just going to make that 60 seconds so I don't have to do dimensional analysis. How many meters? That's asking us for a distance. So a couple of ways you can do this. Our speed formula looks like this. You can go ahead and plug in your numbers if you want, but then you're going to have to do algebra with numbers, and if you're bad at that, maybe you don't want to do that. So maybe before you plug in your numbers, you rearrange this equation to solve for time, which is what I'm going to do. Or sorry, to solve for distance. We're looking for distance, so we want to get this by itself. So to do that, I want to get rid of the time that's over here. So I'm going to do what's opposite. It's being divided by time right now, so I'm going to multiply by time to cancel it out. But to keep both sides the same, what I do to one side, I have to do to the other. So distance equals speed times time. So distance equals 25 meters per second times 60 seconds. I'm going to get 1,500 meters. You could have done the same thing and just plugged in the numbers instead from the start. Oops. So 25 meters per second equals distance over 60 seconds. And you could have just multiplied both sides by 60. It would have given you the same thing. But you can see some of you would get frustrated by the units. And the units do work out perfectly, and they cancel each other to get to the correct unit. But maybe some of you don't like dealing with all that stuff when you're doing algebra. So maybe you rearrange the equation first. Really, either way is acceptable. Just make sure you pick a way that you're comfortable with so you can get questions right on a quiz or a test when these problems get more complicated. Ask your teacher for help if you need anything.